Thank you for being here, and to the people in the web, hola. Especially to Vanessa, who hopefully is in the middle of the night, is watching from Bali in Indonesia. So, hola, Vanessa. I hope the web in Bali is working for you. So here is an approximate outline of what I hope to talk to. Just giving some of the background of my interest and my development of my thinking about small-scale fisheries, and then explaining some of the concepts that underlie our new approach, how the size structure of populations changes as the fishing pressure increases, and then this fisheries concept called spawning per recruit, or SPR. And so that is some of the theory. And then I want to just talk about how searching for the answers for small-scale fisheries. We have, with Adrian, we've developed a new technique for analysing size data, just size data, which we think can simplify assessing fish stocks. And then hopefully I'll get time to talk a little bit about the work we're doing in Palau to illustrate how artisanal fishermen are coming to accept and to use this technique. So for me, this journey, and some of you I know were here 6 or 7 years ago when I was talking, so I hope this will not be aburrido for you. So for me, for my doctoral thesis, I had this question. In Australia, the abalone fishery is very valuable, and we were aware in the whole world that the production of abalone was declining, and we were wanting to conserve our fisheries and understand why in Mexico and the US and in Japan the catches were declining all the time, and we were wondering why it was so difficult to sustain abalone. So I first went and began talking to the divers and learning the fisher knowledge. I was also going to the library and learning the science knowledge. And in the science knowledge was that the larvae of the abalone would move 90, 100 kilometres. And my job for this state of Tasmania was to make an assessment for the entire state. Maybe 400, 500 kilometres of coastline. We were assuming was one stock. And the larva we thought was moving 100 kilometres. And we were expecting, we had one study of maturity and growth, and we were seeing this as a large, uniform fishery, just like the textbooks were telling us for many species. But when I talked to the fishermen, they talked about areas that kept producing and other areas that declined, and they could see these areas closely. Our statistics didn't show this because our statistics were from big areas. But the diver said, in this area, we no longer go there because there is nothing. We go here now. And they call recovery bottom and non-recovery bottom. Some areas produced, others didn't. And began asking my question, why? And so, this is complicated, but we can make it simple. So I set up an experiment where in these central areas I removed all of the adults. And in the other areas, the controls, we did nothing. They were controls. And we did it in these multiple places around the bottom of Tasmania. And these over here, this is all the different sites. But just focus, here is the summary on the right-hand side. So the first with the adults. Before we began, this was the average density of the adults. The two controls, and here the experimental area. So we removed the adults, we reduced the density of adults by this much. So this was the pattern in the next breeding season of adults. And when we came back, this is the pattern of, this was the pattern of the recruitment. So what we showed that on scale, not 90 kilometres, 100 kilometres, but on a scale of 60 metres, we could reduce the recruitment by the adults. And so what was important was the local amount of adults. It didn't matter that there were abalone meters, hundreds of meters or kilometres away. What mattered was the abalone were breeding close to each other and the larvae were staying in the one place. And so we began thinking, this is not one fishery, but every reef is a fishery. And to make, at first we began thinking, well, if the fishermen go everywhere and the abalone breed at the same size and grow the same way, then maybe that the larvae don't move is not so important. But what we saw, so here is a growth curve. This is actually for New Zealand, this information, but we saw the same thing in Tasmania. So here, this is growth, this is age, and 3 different places. Stewart Island in the south, Banks Peninsula in the middle, and here Taranaki in the warm water. And each place has a different type of growth. And for abalone, it is mainly about temperature. In the cool temperature, more nutrients, and they grow. You can see that because where this growth curve bends over is their maturity. So very different size of maturity. And what I'm showing here, this is the legal size. You can only take the abalone above a certain size. And so what you see is these populations here are totally protected. This report concluded, in this area, Taranaki up here, there is no commercial fishery, but there is a recreational fishery. This report concluded that in Taranaki, the recreational fishery is entirely illegal. The Bahoil Taye. But because this is the area that I was commercial fishing, mainly down around here, I know that all of these places, it is poor growth. It is small size maturity. If you come into this area, this beautiful area of Rias, and down on the exposed side of this island, Stewart Island, there are growth curves that are way, way above any that are here. And everything you can take. No, even when you fish legally, you can remove all of the adults. And so now this is the scale of maybe 1,500 kilometres. Now come down to this scale. This from here to here is 45 kilometres, and it is right here. This was when I was fishing here commercially. My house was just here, and this is a very, very exposed coastline, and here is very sheltered. And down here, on the exposed shoreline, the size of maturity is very big. And to begin with, we all fished there because it was easy, good catch rates. But after 15, 20 years, we had removed all the adults and all the larvae, and it was dead. The bottom was dead. There is a bay just in here where we used to take 5 tons per year. And in maybe 2001, the last time I went there, we found 5. Not tons, 5. But now, up in here, where we never fished because there are so many beneath the size limit, it was too hard work and not many that were legal sized, they are breeders, but breeding, they're adults, but they're small. And so now, all of the fishing occurs in here. And but this is one statistical area. So the catch statistics say almost nothing has changed. And so now if we come to this scale here, this is 2 kilometres. And I had a fisherman who was the first fisherman in this area. He mapped where the big size of maturity and the little size of maturity. So the white is a small size of maturity and the dark is very large size. And this area, it collapsed because in abalone, we scientists, we worked in the sheltered places, the places where we could work all the time to study growth. And we didn't understand that in the very rough places with the big waves, the size was much bigger. And so we set the legal size limits very low because we didn't understand that the commercial beds were very different. And so typically right through the world, this has happened. The researchers work in sheltered places and the fishermen fish in rough places. And so the size limit in this place, this is Western Australia, but it was the same as in New Zealand and the same in California. So the fishery collapsed just down to these white places. The other places, they died. And in this area here where we worked with the fishermen who made these maps, they began to use not the legal size limit, above the legal size limit, and different size limits. And slowly they brought this area back so that now it all produces. And it was these experiences which began making me think how complex these natural phenomena, the natural, particularly shellfish. But over time I began, as I worked on other assessments of deep water fish and sharks and lobsters, many species, not at this small scale of abalone, but at larger scales, I began to see this same complexity. Areas where fishermen would stop fishing because now there was nothing there. And always you hear fishermen say, oh, they have moved to another place. The fishermen have moved, not the fish. The fish are gone here, and now you must fish there if you want to fish. And I began seeing it. At first I hoped this was just a problem of abalone. But now I believe it is, at different scales, a problem for many, many species. You know, the lobster biologists used to believe that the lobster in the southern hemisphere, the larvae, would travel right around the world for 18 months and settle back in their places they hatched. And then in the early 1990s, one fisherman found a lobster species that was only on 2 seamounts off Chile. And the lobster biologists went, no, they cannot go all the way around the world and find 2 seamounts. And so now there's been a genetic study done. And sure enough, they find the lobster species, they're staying within maybe 100, 200 kilometres of the adults. And nature has gears and complex mechanisms in the ocean that the biology takes advantage of to remain close to home. And so I think if we conceptually, for all species, so here I'm showing the idea of this is the distance that animals are travelling through their life, and this is the proportion that travel. And I think that all species at different scales, for evolutionary reasons, they maintain long-distance dispersal, because as the environment changes, as habitat is lost, the sea levels rise, they must always be able to find new places. You must have colonisation. But it is like us. A few people move a long way, but most people stay close to home. And so when it comes to managing, and I think we biologists, it is more exciting to look at the longest tag movements. How far did the animal, the record, what was the record? It is not so exciting to think about the average distance moved or the distance that most animals move in 1 or 2 years. But this is the scale that the management has to happen at. And I think when we look across all the species, over the last 20 years, we have been revising our estimation of what this distance is to smaller and smaller. You know, with tropical reef fish, we used to wonder how they could leave the atoll and go out in the ocean, and then how could they find another atoll. But now we know that if you take an area 400 by 400 metres, 60% of the larvae settling came from this area in the first place. They went outside the reef and they found their way back to this atoll and back to where the parents were. With the clownfish, more or less 30% of the clownfish coming to an anemone come from those parents. So finding, like the salmon, we know the Pacific salmon, not only find they go to the Bering Sea for 3 years, they not only come back to the river and the stream, they come back to the gravel bed that they hatched in. And so everything is more smaller and more complicated than we thought. And so for me, this is the challenge. I call it the tyranny of scale. That our management is still happening over hundreds of kilometres in most parts of the world. I think here in Galicia you're a bit different with many of your fisheries, and I think you are leading the world. But for me, this is the challenge that we face globally. That we are, in many places we are now starting to collect our data at a smaller scale, maybe on kilometres or tens of kilometres. But in the case of abalone, the challenge is really how to do things at the scales of metres and tens of metres and hundreds of metres. And when I first came to this for abalone at the end of my doctorate, I was just very depressed because it seemed to me that working for the government, I could never do this. I could never collect the information I needed or make the number of assessments. It was so complicated and so expensive. And so it came to me that, from talking to some abalone divers, the only way this could work was to make it less of a fishery and more of a garden. It should be like grapes or vegetables, and people should look after their own areas and learn their own areas and learn what is the size of maturity here and look after their own self-interest. And the government should have a different role than telling the fishermen exactly what to do. So, looking around the world and realizing more and more that maybe not at the scale of meters for abalone, but for coral reef fish at the scale of kilometers and 5 kilometers, and for lobsters at the scale of maybe 100, 200 kilometers, at different scales, we still had this problem that there were many, many more fisheries and fishermen and fishing communities than the few governments. You know, in government we are small, taxes are rare, and the governments would rather spend the money on schools and hospitals and military. They're not so interested in fishermen and fish and shellfish. And so it seemed at first, I was just very depressed that there was no way this could be done. And then again, talking to fishermen and thinking about changing the way it was done, where fishermen would do this for themselves, I began thinking about it a different way. And it occurred to me that the problem we were facing actually had similarities to the problem that the Chinese government, when they took control at the end of the Second World War, and they wanted to stabilize their country, they knew from Chinese history that the revolution always comes from the countryside, from the peasants, as the communist government themselves came using the power of the peasants. So they knew that if they were to lose power, it would come from the country, from dissatisfied poor people. And one of the big problems for the poor people was health and short lifespan. And so they made this a priority to improve the health of their country, and particularly in the countryside. And their strategy, I think, was very, very interesting and has great lessons for us. And it's what they called the Barefoot Doctor program. They didn't build more big universities and train more surgeons and put lots more money into to research. They actually took people from the villages and they gave them basic training. They understood that maybe 85% of health problems are simple health problems. It's sanitation, clean hands, it's healthy diet, it's from diarrhea and things like that. You need rehydration. It's simple, the things we all suffer from, the simple things. And they trained these barefoot doctors in these techniques, what to do with those things, and sent them back to the village to work with their communities. And so it seemed to me that what we needed, confronting the problem of the world fisheries, were barefoot ecologists. This isn't to say that there isn't need for researchers and government. The government is needed to set the standards and to audit to see that things are happening, that the catches remain stable and high for a country. And the research is needed to train and to develop techniques and to understand the complexity of the environment. But for the everyday things, we need more technically trained people. And I think, you know, I love to read about and talk to you about what is going on in Galicia, because I think here in Galicia and Chile and Japan, there are places that actually are practicing this model. And so what we're talking about is really more generic expertise, general expertise, and facilitating communities to do the simple things, to monitor themselves, to collect data in the long term, and to change the way people work, and to treat the fishers, give them the status they deserve, which is they are the local experts. They understand their local conditions and what is happening. So this is really about motivating fishing communities and facilitating fishing communities. And for me, the context of this has to be that the individuals, the fishers, must have incentive They must have a motivation to do this. And their self-interest must be aligned with the interest of the resource, what's good for the resource. And so for me, the context has to be that none of this toolbox, none of the Barefoot Ecologists, none of it will work if everyone is acting as pirates and raiding and going everywhere and stealing from each other. There must be a system in the law where people have ownership, they have their secure access rights. They know that not only for the rest of their generation, but for the next generation, their children and their grandchildren, if they want to be fishing people and in this fishing community, what they do now, the sacrifice they make now, will pay off for themselves later and for their children. So there must be security. And for this, many ways this can be. For the communities in Australia and some countries, we practice it more at an individual level with individual transferable quotas or a whole range of things. I don't think we make enough of territorial user rights fishery, which I know is the basis of a lot of what goes on here in Galicia. And Chile as well, and traditionally it's been the main basis in the Pacific as well. But the European colonisation has broken those systems down. And I think for many of our species, which are so local, really these territorial user rights is the way forward. And then within that framework, then I think the provision of technical services. So in my words, the Barefoot Ecologist. And here the emphasis I think is less about the biology and more about the working with human communities and human nature. So we're talking agents of change and building social capital, educating people, learning from the fishermen themselves and reflecting the information back. So this is un poco broma, the big words, ethno-socio-quantitative fishery. A generalist, someone who's not maybe will never publish a scientific paper, but understands the complexity and the breadth of fisheries, that it's biology with human nature, and the two must come together. So empowering fishing communities, and this is actually a slide I made up for talking in Japan, where Japan also has these regional, local community-based management, but they're so focused on aquaculture and putting more seed in the water and not enough with changing the behaviour of the fishermen. And so this is my technology of the mind rather than just more technology and hatcheries and that sort of thing. So obviously an essential ingredient for this is that there must be simple ways of doing assessments, rapid assessment, and this phrase that Bob Johannes coined for the Pacific, dataless management, which is really, I prefer this rule of thumb management. So these may not be precise assessments, but they are still scientifically based. They use general knowledge, they use the fishermen's knowledge. They must be based around things that fishermen can do. And in my experience of working many fisheries, I think once you come to know how the fishermen work and spend time on their boats, spend time diving with them, there are normally some way, some little thing that can be done every day to collect a little bit of data. And if you have many, many fishermen, maybe just measuring 2 or 3 fish a day. In one fishery we worked, a lobster fishery with traps. We put a marker on one pot, one trap, and the fishermen who participated, they undertook to measure the lobsters out of that one trap every day. Maybe just 1, maybe up to 5. But at the end of the year, we had 45,000 lobsters measured. A little. And then ways of assessing this information. And so really the rest of the talk, what I want to talk about is really this technical challenge. How we the tools, the simple tools, and I think we now have the answer of how we can make very simple assessments that are still very powerful and useful in the context of fishing communities. So before going on to that, I want to just make sure everyone has a couple of basic theoretical underpinnings, some underlying concepts. So the first is the way that a size structure of a population changes when we fish. This is a very basic to fisheries assessment. It's used in assessment models. In current assessments, it's one form of information that tends to be analysed. In our technique, it is the main, really one of only two types of information we use. So when a fishery begins, so here this is a conceptualisation of a size composition, length, frequency, or doesn't matter, weight or length, more or less it's the same. And so here we have from small to big here, and here this is the frequency, the count. And generally if you go, when a fishery just begins or before it begins, if you go and measure the fish, you'll see that most of the fish are some sort of middle size. Not many fish are small. The small fish have to exist, obviously, to have this many big fish. But generally, most fishing techniques are selective to some extent. Either the mesh size lets little fish through, or the little fish live in a different place, or the fisherman it's not worth catching lots of little fish. So generally, if you look in the market or look in the catch, you'll see very few of the smallest fish. Most are middle size, and then there are a few very big fish. These are the old fish. And there are very few of them, even if you go and look on the reef or in the ocean. There are very few of them because very few fish get that big. The growth slows down, and natural mortality means they die off. So these fish are actually rare. And then when you begin fishing, what you see is a deformation of the size structure with the large fish. Less fish are getting to live that long and get that large. And so here I'm showing it with a number of boats. As the fishing develops, as the pressure develops, the deformation comes from the right-hand side. And so if you think of this as an average, the average is getting smaller. The average size is getting smaller. And if the fishery continues to develop, the process continues. For quite some time, this left-hand side will stay the same, because there are, as long as there are enough adults breeding to keep supplying, keep replacing themselves, you'll have this, this is what we call the selectivity curve. This selectivity curve will hold the size of the little fish steady, but there'll be less and less of the big fish, and the average size will get smaller. And that process continues as the fishery develops. Now at some point, if the fishing gets too heavy, you'll see this happen, that suddenly the left-hand side will start deforming as well. And that is the sign that your supply of little fish is now declining. This is what we call recruitment collapse. And if you don't start managing, that process will continue. And when this process begins, then the absolute amount of fish starts declining. The catch rates go down, the total catches decline. And if you don't stop this process, you are on the path to local extinction. So, in assessment terms, what we're interested is understanding how much spawning is happening in the fish that you have left. You know, in a size sense and in a proportion of spawning that an average fish is doing, that when the size structure looked like this, they were getting 100% of their natural spawning. And so the question for assessment is how much is this in here? How much spawning is happening in here? And is it enough? And so that is this idea of the way sizes change. That's the first concept I want to think about. And we'll come back to this, how we work out whether it is enough. And but the second concept is this spawning per recruit. Let me go back here. So we could think about when the size structures this. So here I'm not talking so much about the amount of tons, but just the size structure you would see by going and measuring a catch and looking at the proportions. And so you could think of when the size was like this, on average, each fish was getting to do 100% of natural spawning. So we call that 100% of spawning per recruit, 100% SPR. And the question is how much of on average, is each fish getting to do with fishing? So let's just talk about spawning per recruit, SPR, a little bit more, because this is the basis. This is what we can now assess just from size data, and which hasn't been possible. Previously, you've needed size data and age data and growth data and a model to work this out, but now we can do it direct from size data. So this is a definition here from Walter Martel, that this concept SPR has had many names and has many names: spawning potential ratio, spawning per recruit, or eggs per recruit, or proportion of lifetime egg all the same. Let's just think about it, SPR. And so the definition is SPR is compared to no fishing. How much spawning on average is each individual getting? The average individual, when under fishing, how much is it getting compared to the unfished? Unfished is 100%. And it is a relatively old concept in fisheries science. I would argue a very good concept, but as we've got more power in models and more technical, we've tended to model the population in numbers or tons as an age-based model, and we've got more complicated. So now most of the assessments are focused on trying to estimate the amount of biomass, whereas this is it's a more rate proportion thing. It's not directly, it's linked, but it's not directly related to the absolute amount, the biomass. It is a concept that it's based around the, where am I? It's what we would call F. It's a concept based around fishing intensity rather than biomass. And the beauty of it is that it's been studied by meta-analysis. Studies have been made of the very data-rich assessments, and we have benchmarks or reference points we know that a certain level, we can tell from the science that a certain level of spawning, average spawning per recruit, is likely to be sustainable. And within fisheries law around the world, we have these reference points already in place. So let me try and give you another picture of what we mean by this spawning per recruit. And let me use the example of human populations and predicting what will happen with a human population. So the complex, expensive way of doing this that most of our nations use is through the census, where they try and actually, every 10 years or 5 years, they actually try and measure how many people are in a population. And this is rather like the current stock assessment, is trying to model with age-based models the absolute tons or number of individuals in a population. And it is, in a census sense, it is very accurate, very expensive, a very good way of proceeding. But a simpler way of doing it is just to do a simple survey of how many children each couple are having. And we know that if on average every couple is having 2.1 children or more, around about 2.1 the populations are stable. And so the problem with Europe, or one of the problems for Europe at the moment, is that less than on average couples are having less than 2.1, and so we're seeing without immigration the populations will decline. And above 2.1, so in countries through African countries and less and less, but Asia, but some Asian countries, we're having more than 2.1 up to 5 or whatever. And so there we can predict that the populations will grow. So in this way we cannot actually say how many people are in a population, but we can feed back to fishermen what is going to be likely to be the future. And so the important concept here is replacement level. So there is a point where we think it divides between a population that will increase and a population that will decline. And so I want to make a parallel to SPR, that SPR is in some ways similar to this. But in the human situation, possibly on average, I don't know what 100% of breeding potential is. Maybe it's 10 children per couple or something like that. I'm not sure of that number. But here the benchmark for biological populations is without fishing 100%. And so we know from meta-analysis that the replacement level is somewhere around about 20%. In fact, the species are different. Sharks and things like that with a limited number with a defined number of offspring every breeding, they could well be quite a bit higher than 20%. And we know that some of the very productive teleosts, it may be as low as 10 or 12%. But across the meta-analysis, let's just think about these numbers. Around about 20% is the replacement level. And in international law, unless you have a well-developed stock assessment, they generally tend to say this is the reference point you should use. You should not, this tends to be called a limit reference point. You should not go below 20% SPR, because then you are putting your fishery at risk of decline. And for most, in fact, the proxy for MSY is between 30 and 40% SPR, and the proxy for MEY, maximum economic yield, is about 50% SPR. So we have these reference points, and this is the concept that we are using. So let me now just go back to the story of how we evolved this idea, and coming back to the idea really came slowly from working with divers and abalone. And so it was actually the diver. I don't know if you remember that map, the small scale map with the black and the white. It was that diver who mapped that area for me that told me that stop worrying about size and look at the shell of the abalone, and you can see what is immature and you can see what is mature. And then if you want to manage, then you mustn't take all the adults. You must leave mature adults everywhere. And so he had a formula in his head that every time you stopped at a place, you must look for yourself what's mature, what's immature, and you must leave at least 30% of the adults in each place, regardless of what the size limit was. And I realised at first I thought, nah, this isn't scientific. But then I went back to my own biology and I saw what he was saying, that the abalone, they are, when they're immature, they hide under the rocks in crevices. And so their shells, they're flat and they're skinny, and they have no growth on them. They have no fouling, no epiphytic growth. But as they mature, they come out from the rocks so they can join the breeding aggregations. And their shells become fat and round, and the light lets the epiphytic growth go. And so you can see the adults and you can see the juveniles. And you can learn, in a place with big juveniles, the adults will be even bigger. And you shouldn't use the size limit, because then you can remove all of the adults and all of the juveniles. But in other places, the adults are small and the juveniles are even smaller. And there you can either use a size limit, or sometimes there's nothing up to the size limit. And so from my own commercial diving, I began testing this. At the end of a day, I was swimming places I didn't know, and I'd look at the abalone I was collecting, and then I'd get aboard the boat, and in the evening I'd talk to the divers, and I said, what is happening here? What have you seen in 20 years? And I could predict. I could get on the boat and saying, this area is bad, it's going down. And they say, yes, every year we come back, we have to move the boat more often to make our catches. Other areas they'd say, oh no, I'd get and say, I'm leaving. The size limit here makes me leave a lot of the adults. So this area must be stable. And they say, yeah, we do the same thing now that we did 25 years ago here. And so I could see that this was correct, that there was this change in the shell, and that from this long, skinny, and this isn't so different to humans. Think about the young teenager who goes tall and skinny. He's 13, 14, 15. Maybe he's just becoming mature, but hopefully he doesn't have any children yet. And then by 25 they're starting to get shoulders, and by 35 gordo. This is just what you say. So there is this period here. So this is the range. So these are abalone that I took out of one cave. They're all from exactly the same place. And these ones here are right back in the cave, and these are, these ones are sitting in the open. These are full out. And so this is roughly the age and length. So this is length versus age. Here is the weight versus age. And here is this spawning per recruit versus age. And so we worked out that we could see that here at this size, just as they were beginning to mature and the growth curve, these are the animals here. And then and here, up here, these are the animals that are starting to have done most of their spawning before we catch them. But the very exciting thing is here, there is this period here, just from when they mature, where every year they are doubling in weight. And this is true for all species. that from the time they mature through to the first few years of their adult life is the time they gain weight the fastest. They gain weight very, very rapidly, just as they mature. And so there's a great benefit here for fishermen. You know, when you get to the point where there's no breeding, then you begin recruitment decline and collapse. So you must avoid this point. But by this time, the catch rates are low, the fish are small, they're not so valuable. There's a great benefit to work with the fishermen to preserve enough breeding, because then every animal is heavier, 2 or 3 times heavier on average. And it's very, very quick. Normally, if you can just delay, in this case, if you can delay from catching every abalone on average at 5 years old to catching it at just 7 years old, there's a 250% weight gain to be had on average in just 2 years. So in the time is different, animals grow at different times, but this equation is the same, that from size of maturity to the point where they do maybe 30% SBR or 40% SBR, there is a huge weight gain and a huge gain in catch rates and value of the catch. So anyway, we use this idea, we taught this to divers, and you don't need the detail of this. We just made a simple decision tree about, did they think a catch in an area was declining or going up, or was it stable? And then what did the shell look like? And so from this, just in a workshop, just using common sense, we had these 8 categories of is it very depleted? Was it depleted a long time ago? Is it an area that, back here, number 8, is an area that was never had productivity? And in here about 6 is where we don't do anything because it is good now. And if it's less than 6, then we should either be careful or we should be reducing. Or some of these areas where the size limit was too big for those areas, we should be fishing harder. And so through these assessment workshops, just getting fishermen, teaching the basics, teaching them about what the shell looks like. And what we found was the fishermen were excited by this. Some of them said, I've been swimming for 20 years and I've never understood why some areas go bad and others are good. It's a mystery to me. And now I understand. I'm excited. And over 2 or 3 years, these workshops really gained strength. And after 2 or 3 years, they were starting to say to the government, when we began, they were saying to the government, we don't believe your stock assessment. It's a black box. We don't understand it, and it's wrong. And we don't want our catches to go down. And 3 years later, when for each reef, they were saying, yes, this reef is good, we should keep the catches the same, but this reef's not going so well, we need a little bit less here and a little bit less. And then they would come to the end, and they said, the government's giving us too much catch. We don't have anywhere to put this catch. And so they started asking the government to reduce their total allowable catch because they were starting to relate to each of their spots and wanting to have the right level of catch. They were wanting to bring back the areas that were bad. And so the government turned around and said, well, we don't want to use our model anymore, and we'll just start setting our catches from what you people... We will watch your process, and if your process stays good, we will just do what you say. And so I published this and about abalone, and the journal, they said, how does this... It's a nice paper, but we want to say something more than just about abalone. How does this apply for other species? And first I thought, this was my life work. I was happy that I'd solved a problem for one fishery, and now they want the rest of the world solved as well. And it made me think. First I just wrote them a few sentences, and they published the paper, and basta. And then after a time, I began thinking of an analysis we could do. But so I'm a consultant, and I only get paid for work that people want to pay me for. And here was this analysis I was thinking of that we could test some ideas, but no one would pay me for it. And it was a bit risky, a bit dangerous. So one summer, I had a student who wasn't doing very much. And so I said, and he wasn't ready to start his PhD, and I was going on holiday, and he was thinking about getting a job. And I said, here, try this analysis for me. And when I come back from my holidays, I'll see how it's gone. And when I came back, I said, do you think I'm crazy? And he said, no, I think there's something in it. So we did this analysis where we got information for many, many species. And we made these models of SBR. So the question we were asking is like with the abalone we could get our eye in. From the size of maturity, we could get our eye that we needed adults this size. And if the little... So it seemed to be relative, the amount of spawning seemed to be relative to the size of maturity, or relative to the maximum size. And so we began asking this question, do all the species, are they all the same? You know, is it the same multiple of their size of maturity? Have they all done the same amount of spawning, the same amount of SBR? What is the relationship between SBR and size in a standardized way of size? So we gathered a lot of information from the literature, and we had a very high standard. They had to be very good, very solid estimates. We didn't want approximations. And so for these SBR models, and this is the way that the science has been done, so if you want to estimate SBR, you need these models or even more complex. And so the important, there's growth in there, and there's natural mortality, and there's size or fecundity. So I want to point out this is a growth equation. There's a couple of, you don't need to understand this, but there's a couple of parameters here that I'm going to come back to and use. So first of all, growth is described in terms of, this is L infinity, this is the average maximum size that an animal will get to. And then there's this K here. This is the steepness of the growth. So the juvenile growth, how steep is that juvenile growth? And then the L infinity is where the growth slows down in the adult size. And then the other value, natural mortality, we call M. So that's really the rate at which the animals die off. And then LM is the size of maturity, the length of maturity. And those are 4 parameters. You'll see why. I just want you to see where they are in those equations. You don't need the equations. So we gathered together. In the end, we had, in the paper we've just published in ICES, it's on the web at the moment, but not in the paper yet, we had 123 species. And everything from shellfish to shrimp, to whales, to sharks, to teleos. And we were thinking that there was just one relationship between size and SPR. And so when we saw this was our result. So every one of these lines is one of our species. And here in this one we are, so the standardized weight, but this is the maximum weight is 1. And this is SBR here. And we were thinking that maybe it would say, and at first we seemed to see a lot were in the same area, and we were hopeful we were right, that there was one relationship. And we kept saying, oh no, these ones that aren't on that line, they're wrong somehow, they're wrong. And then eventually we were forced to accept that this is the natural variation. And for a while we thought, oh, well that didn't work, did it? But then we started looking at why is there this variation? And we started seeing that there were different types of species in here. And so this is one we started just calling type 1. And so look at, this is the ratio that M over K, mortality divided by the steepness of growth. And we realized that all the animals that had a M over K ratio above 1, they are what we call more opportunist type species. So do you know the concept of, ecological concept of R and K strategist? So the R strategists are the population can grow very fast, but they crash. They're very unstable populations. These are, in plant world, these are species when you clear some earth, all the R strategists grow away. They're the weeds. And the K strategists, they are we think of them as long-lived. Really we're defining these concepts differently, not so much in size and time. So the K strategists are actually the ones that grow rapidly to their maximum size, but then they breed many, many times around their maximum size. These R strategists, they start breeding at a small size and they never really slow down very much in their growth. And almost none of them get to be their average maximum size. That's a theoretical conception. So we began seeing that these were first the type 1, the R strategists, and then the K strategists. And the first group of K strategists, indeterminate growth is where growth never stops, but it becomes slower. As you put more energy into breeding, you grow more slowly. And so, you'd never stop growing. And so these are K strategists, the blue is K strategists with indeterminate growth. And then we have the what we call the type 3, which are, these are K strategists as well, but these animals grow rapidly to their maximum size and then they never grow once they start breeding. So these are more like the mammals, but we realise, and we see some shellfish and some fish that do this as well. And so we realised there was actually some pattern in here. It wasn't just a mess. There was some predictability that you could start, if you knew something generally about a species, you could start seeing what the relationship was between how much spawning they'd done and how big they were. And more than that, we realised that we were actually following on this idea. I don't know whether you know this concept of Beverton-Holt life history invariance. So there is if you don't know much about a species, in the literature, one of the ways, so say you want to model a population, but no one has ever measured mortality. Well, it's been worked out, and the theory is that because evolutionary puts constraints on, obviously you cannot begin breeding before you grow. You know, you have to grow first and then breed. There are some evolutionary constraints on how you do your life cycle. You can't breed first and grow later. And so breeding is really a process of growing to advantageous size and then starting to put your energy into breeding. And so it's been argued that there is one formula that works. And so that these basic parameters here, M over K and this LM, size of maturity divided maximum size, it's been argued that these have relatively fixed values. And there are a lot of papers trying to estimate exactly what these values are. Well, what we realised, or what Adrian realised, was here, this is this black line. This black line here was the one we were looking for. It is, if you believe this, which most of the literature believes this, and many times people are now estimating M from this formula. They can measure growth and they get K, and then they can say, well, M must be 1.5. I mean, M over K must be 1.5, so M must have a certain value. And what we realise, which other people haven't, is that if you believe this, then every species does the same amount of spawning at the same size relative to their maximum size. And what you see here, though, is it's not true. Species are different. Whether you're an R strategist, you're on one side of this equation, and if you're a K strategist, you're on the other. And this value, this equation, is actually, it's like the average number of children people have. No one has 2.1 children. You know, people have 1 children or 2 children or 4 children. And so this is just some average that you get by not understanding this complexity. And so here we have, what I'm showing here is very quickly is this is, if you look at weight, standardized length. And so these equations and these values you get from being related to R or K strategist define these curves in weight and length and even in age. And here, look at this one where, you know, these ones, the lines cross each other. So here, what we've done here, 0 here is the size of maturity, and 1 is the maximum size. And these are smooth. This is a family of curves, and all this is just from this ratio M over K, high M over K of about 4 down to a low M over K of 0.1. And you're probably wondering, why am we talking about this? Well, the point is that the size composition of your population without fishing, and even with fishing, is determined by which one of these lines. So this is M over K4, and this is M over K 0.1, and then here, this is modelled size structure. Here, this is M over K4, this is M over K 0.1. This is size structure without fishing. And so what you see is the R strategists, they have populations that are dominated by juveniles, and they do not form an adult mode. But a K strategist, they have populations where juveniles are actually quite rare. And when it's unfished, there's a very prominent adult mode. And so here, you know, this understanding what the size structure of an unfished population is like gold when you're doing stock assessment. But we never have that information because no one began studying the species before they started fishing. So here is a way where theoretically we can get back to a benchmark. You know, this gives us some way of comparing the modern fished size structure to what it should have been. So we realised when we got to this point that we had started having a way that we could actually make assessments just with size data without having a time series going right back to the beginning of the fishery. we could predict. And here's a way that you can say, well, we know this is an R species. This is a herring or an anchovy or a tuna. So we know it must have originally had a population looking like this. You know, this is a groper. And so we know it's got a population that would have looked like this before we began fishing. And so this starts giving us a way into making assessments. And more than that, we've discovered that it's very well established in the field, in the science from Beverton and Holt, that here this is these two ratios, Lm over L infinity and M over K, they're actually related to each other. So that means that without, you come to a population now where it's been fished for a long time, you cannot see what the average maximum size is. No, sorry, the other way around. We cannot get the M value. But if we can actually see the ratio between the size of maturity, which we can measure now, and we can look for the biggest fish that's ever caught, you can start getting estimates of this L infinity. And so you can start from one can inform the other. And these are a way of starting to do data poor assessment. So let me show you here. These are species from our assessment, but let me show you these. So these are the curves of the species in that last slide. And what you see is these groups, they start coming into bands. And that's what we're seeing. The family groups tend to share a similar relationship. And they would have had similar unfished size structures. And so this is a way we can start actually, without having studied a species or a population, you can use something that's known about that family or that species somewhere else and borrow that information and bring it into your confradia or whatever where you haven't done the work. And compare, this is the dotted line is the Bevan and Holt. So this is actually a line that's being used. Currently, if you do data poor assessment, you will actually assume all the species follow this one line. And if you're doing that, you're assuming a certain thing about the productivity of that species, how much spawning they've done in a certain size. And you can see all these species down here, they do a lot less spawning at any size than would be assumed by Bevan and Holt. And so just by mapping out from the literature, meta-analysis, where each of the family groups lie, we can start making better predictions about their size and their productivity. I was going to make another point there, but I've forgotten what it was. So, so here is a way we can start making our assessments. I'm starting to run out of time. Let me just illustrate carefully how we try and give you a mental illustration of how we can use this. So this is a band, call this Lithrinids, tropical emperors. This is their generalized curve. This is like an average curve for an emperor. And but at the moment, this has no scale. This is just relative to maximum size. And here, this is the percent of spawning SBR. So this is the size of maturity. And so from this relationship, bringing this to a species that we haven't studied before, we can say, okay, well, in the local situation, we know that they will have this generalized curve. And in the local situation, we can actually do a size of maturity study. That's pretty easy to do. And so that will give us a point that we can fix this curve. This can then become an absolute curve. Size of maturity can be 40 centimetres or millimetres, whatever. And from that, we can have, remember, behind each of these curves, there's actually a size structure that's predictable. This curve implies a certain size structure. So let me just show you in a theoretical sense how we can use this information. So we start off in a situation where we know we have a certain species. We haven't studied it in this situation, but we know it has a certain form. And so that's our one assumption we begin our assessment with. And then we get the size of maturity, and we say, okay, this generalized form this becomes an absolute curve by fixing the size of maturity. And then we go and collect size data from the fishery. In this case, we're talking weight, but it can be length as well. So then this is our two pieces of data we're collecting. We go and collect, to start off with, size of maturity. That lets us set where the curve is in absolute size. And then we collect our size data from the fishermen, from the market, whatever. And then in schematic of how this assessment works, from this curve here, this implies a size structure. So what if you think about what is the step, what is the increments up this curve according to size class and plot this. So this is now weight class, and this is now the amount of SPR per weight class. So this is implicit in this curve. And here, this is weight by numbers, weight class, numbers by weight class. Well, spawning is generally proportional to adult weight. And so if you convert this curve here, just by multiplying the numbers in each weight class by the average weight of that weight class, these curves are comparable. This is the unfished, this is the fished. And then you just need a clever student to work out how you can fit the shapes together. We know this shape here, over on the right, this shape here, this change in shape compared to this is determined by fishing. We can actually model what that is. And so we can fit, with a shape fitting routine, which is what the software have, we can fit those two curves together and compare the shape. We know this is this one here. That's 100%, and this is something less. And so in this case, in this example, I think the answer is 27% or something like that. So this is where we have software now which can do this, and this is what we'll do in the workshop tomorrow. We'll use some of the local data, and we'll use this software, and we'll start producing estimates of SPR. And so from this, you said approximate, 5-10 minutes more, is that all right? So I'm going to get very soon on to just how we've used this in Palau. So just to recap this technique and what we can get. So we have from the literature, we can understand the different types of species and what their characteristic relationships between SPR and size are. And we can, for more or less any species, we think from its family affiliation. I remember what I was going to say before. Not only are we seeing families have characteristic bands up here, but we haven't got enough to publish this yet, but we seem to be able, within a family grouping, we've seen from morphology, we seem to be able to pick whether within a family an animal will have a high M over K or a low M over K. So if you have a small body size in a family, you'll have a high M over K for that family and a certain size of size structure. If you have a big body size, you're low M over K. If you are tall in your body shape compared to a cylinder, cylinders have high M over K, and tall body size has low M over K. So we think that by building up our meta-analysis, we can start being very, very predictive about species that we know very little about, just by knowing taxonomic linkages and where it sits in the spectrum of body size and body shape. So we think we can start really borrowing a lot of information from well-studied species and start applying it to populations and species that are not well-studied. So anyway, so assuming that you can determine which curve is characteristic of your animal, this is the abalone curve. Then from that you can pick your unfished population, and from that you can make assessments of one, what the level of SPR is, or you can set up a target for fishermen, that the size structure should look like this. And then the fishermen themselves can start seeing the average size is getting small, we need to pull back. Or the average size is getting bigger than the target, so we can take more. And we can also use this to set up size limits as well. So in this case, the fishermen in the Western Zone of Victoria, they want to maintain a population with 50% spawning. But if you just let them achieve that goal with how hard they fish and no size limit, we find that they'll get a 20% less yield than if you give them a size target, size limit that protects 30%. So we set the size limit at 30%, and then above that size limit, so they have reasonable catch rates, they have another 20% SPR. So we can start doing all of this sort of thing, set up assessments, set up harvest control rules, and start having simple control rules and simple management decisions made by fishing communities, just looking and watching their own size structure. So just to finish, I want to give you a little example of in the real world how we're using this. I can't tell you yet that the fishery has recovered because it's still early, but just I think what's important here is how the people themselves are taking to these techniques and how we're being able to apply it. So it's a tiny little island here called Palau. This is the Philippines here. Tokyo is about here. It's a little, only about 50, 60 kilometres long. It's the top of a mountain, seamount, about 30,000 people. And the Nature Conservancy asked me to go there, I think in 2011, and see whether we thought this would work. So this is an area that's actually had, for over 20 years, it's had 40% inside marine protected areas. But the benchmarking studies and the fishermen are saying that the protected areas, they look good, but the areas outside look terrible, and things are getting worse. And so in November 2011, I went there just for a scoping trip. I thought it was for me to see whether it was a good area to work. I found out later it was so they could see whether I was a good person to work with. Fortunately, we liked each other's. And we had our first lot of community meetings. They're very basic. People are actually pretty basic conditions, but relatively, for this area, relatively wealthy populations because they have a lot of American money going in, pretty high standard of education. Everyone talks like a marine biologist. They're very, very smart about fish and know everything about fish and fish behaviour and how to catch fish. And unfortunately, since the Second World War, the fishing equipment has just been too good, and they are too effective at catching. And and in the very first meetings we had, they began saying, because we were talking about the shallow reef fish, and we can't measure how much fish they catch. We can't really control how many people go fishing when. And so in terms of management, they came to the fact that they thought they could catch and release when they catch things on hooks because they're not coming from deep. And also the spear fishermen, they thought, could start learning to only shoot above a certain size. And we all agreed that if this approach can't work here, then it really can't work anywhere. So that was a scoping trip in November 2011. And then in August, I went back and they had selected 12 people to do an initial course. And they arranged the selection of people. I mean, let me just backtrack. So the elements I think that really make this work is here. This man here. He's been a fisherman all his life. His name's Noah Idiong. He's been the president or the speaker of their lower house of parliament. So he's a national leader. He was the man who was very instrumental in getting the MPAs in 20 years ago. He's been concerned about the livelihood of fishermen ever since, and he's a national leader. And he's like the godfather of our process. So it's not as if we are outsiders coming in. I'm an outsider, but this is their own process that they are using me as a consultant for. So then we had this workshop where we sat, and we had from a young fisherman and a middle-aged fisherman to this man here, Harper. He's they're all fishermen. They all fish, but they're not just fishermen, if I can use that. So 5 minutes more. Yeah, 5 minutes more. And so Harper is a advisor to the governor. He's an ex-science teacher, an ex-headmaster. So we did everything from learn how to measure fish to making the measuring boards. And then we started collecting data, studying size and maturity and size composition. The one thing I hadn't expected was they had no idea what was mature and immature. They didn't even know how to tell that. They know everything about fish, but they didn't know that. And they found that a revelation. We did things very simple. We just simplified things. So we just measured through rather than worrying about standard length or fork length, we just told them to measure through the middle of the fish. And we taught them how to tell what was mature and immature. And that, as I say, that was a revolution. And I think has changed behaviour more than anything. And we also had to set up data sheets in Excel and learn how to... And the tropical reef fish, the taxonomy is a nightmare. And as well, we have to, because the fishermen are measuring, we have to work in local names. So we had to straighten out local names and scientific names. There's one parrotfish where the juveniles, the females and the males all have different names. And yet, when it comes to blue parrotfish, 4 species all have the same name. And so we're sitting together, working through these issues. And then we started the measurement, started collecting data. Here is one of the best groper fishermen in the country, learning and absolutely amazed to realise that everything he's catching is almost everything is immature. And so at the end of 2 weeks, we had 914 fish measured from 82, I think, species, but a few species which are most prevalent. 5 minutes more. And one of the first things we saw, this is the size of everything we caught. And what I'm indicating here, this is the size of maturity for some of the species. And you're seeing that for many of the species, nothing is getting big enough to be breeding. And what we saw down here, over across, just from this first trip, 61% of what we saw in the catch was immature, had never bred. And the 39% that was mature was only just mature. And really, without making any further assessment than this just hit the plough, and they absolutely understood what was going on. And really, the assessments we made with our technique were really for our satisfaction. This simple statistic was one they kept talking about. So we reported back, had a second round of meetings, and said what we're finding. And then I went away and left them measuring fish. I was able to make 6 initial assessments by March when I came back. By then they'd measured almost 2,400 fish, and I could make 6 first assessments. And so the assessment consists of, here's a pretty ugly looking size of maturity ogive, but still enough to start letting us fix the size of maturity for this species in here. And interesting, across the board, most of the work on these tropical species has been done in Australia on the Great Barrier Reef. Almost no research in Palau. But across the board, what we're seeing is in Palau, the size of maturity is 20% bigger for almost all species that I've looked at than Australia, which I think is how close they are to the nutrient-rich deep water. And now I'm working in Solomon Islands as well, and I'm seeing again that across the board, the size of maturity across the species has the same relative position. So there, in Solomon Islands, it's closer to Great Barrier Reef. And so we're seeing these broad patterns in something like size and maturity. So here's for this one of the most important species. Here's the lengths we measured for reference sake. This is where we think the average maximum size would be. Here, if they were getting on average 10% spawning done, would be here. And this is our simple form of assessment here. So we come out with an SBR. This is Adrian's software. This is the software we'll be working with in the next few days. SBR of only 2.1%. And F over M of 7. So F over M, fishing mortality divided by natural mortality. Generally, MSY proxy we think is about 1. But what the fishermen really aren't that interested. They're interested in that number, but they're not really interested in those graphs. What they're really interested in is these sort of graphs. Just implicit in all that work are these simple graphs between showing the size, they work in inches, and the amount of spawning, and showing, well, this is what they would achieve, and this is what you're achieving now. Whoops, sorry. At the same time, I was then able to start using enough of the synthesized biology to start informing them about what I think the size of maturity would be. And also potentially there we're talking about a size limit of about 20% SBR. So start informing them about what the size limits possibly can be. So we took that back into a third round of meetings. And let me just show you a very simple graphic that really the people are relating to. This is the whole village. And we say, well, imagine that it's a garden and you have an empty garden and you want to make it productive and you decide you're going to grow pigs. So you would go to the market and you'd buy little pigs and you'd grow it. And it would make absolutely no sense then to kill it and have a pig feast. What you'd do is you'd have young pigs. And I'm told in Palau that it's normal to have 1 litter, 2 litter, 3 litters, 4 litters, and then you eat your pig. Well, this is just common sense. People get this. And we're just using very, very simple things like this. Just the number of saying, look, 61% of what you're catching is never bred. It's like the pigs. So by June we had 2,700 animals measured, and we started holding high-level meetings with the 2 states we're working with. So there were 2 states that were arguing about an area in dispute, and first of all we'd been holding the meetings in both places and getting their suggestions of what we should do. And their suggestions, their options of how to manage things were all very consistent and very reasonable. Some of them are easier to do than others. They can't measure the catch, so I don't know how they can manage a quota. But coming back to establishing size limits and seasonal closures, a whole range of things, managing the gear. And then we brought the 2 states together with all the high-level leadership, state governors and speakers. Very, very interesting. They have traditional leadership and democratic leadership. And interesting, the traditional leaders, it's the male chiefs who make all the decisions and generally do the talking. But there's also women chief, and the women chief are hereditary, and they appoint the male chief. So the male chiefs get to do the talking, make decisions, but as long as they're doing keeping their appointment from the women chief, who can't be sacked, they can't be. So the women generally don't say very much. It gets said at home. And it was noted that in our meetings, the women, the high-ranking women, were particularly outspoken. And the reason they gave for this is that normally fishing is a men's business and we let the men make the decision. But this isn't about fishing. This is about our future and the future of our children and so we should be saying things. And so one of them said, you men should come and work in the gardens for a year and give the reef a rest. And anyway, so they agreed that they wanted to start introducing size limits, and so they're going to have closures for 5 or 6 species at a time, let the fish recover, and then open for those species with a size limit, and then move on to species. So now we have about 13 species assessed. We have 3,700 fishermen, and so these are just the last couple of slides, just giving some comments from some of the Palauans. So Stephen Victor, who's the director of Palau, writing to his international director of marine resources, these are his comments. The method was well received in Palau, and we've been able to collect enough data for some species that we can begin to discuss management options. The technique is very simple, so that every fisherman who has been handling fish can implement. The data analysis seems very straightforward. The results just reinforce what the fishermen knew about the fish decline. The data just made them understand how the fishing effort is leading to the decline, particularly them understanding that 60% of the fish they are catching have not had a chance to reproduce, and that some of the species are only being allowed to reproduce at 2% of their potential. Basically, they realise they are not giving the fish a chance to reproduce, and if they continue to fish that way, there will be no fish for them. And then I like this comment from Harper, sitting around in a boat, talking for a camera. And he said, "We knew the house was burning down, but we did not understand why. And now we know, and there are many things we can do about it." And that's really the end. I think we can go there. Thank you. Fisherman, who was the first fisherman in this area, he mapped where the big size of maturity and the little size of maturity. So the white is a small size of maturity and the dark is very large size. And this area, it collapsed because in abalone, we scientists, we worked in the sheltered places, the places where we could work all the time to study growth. And we didn't understand that in the very rough places with the big waves, the size was much bigger. And so we set the legal size limits very low because we didn't understand that the commercial beds were very different. And so typically right through the world, this has happened. The researchers work in sheltered places and the fishermen fish in rough places. And so the size limit in this place, this is Western Australia, but it was the same as in New Zealand and the same in California. So the fishery collapsed just down to these white places. The other places, they died. And in this area here where we worked with the fishermen who made these maps, they began to use not the legal size limit, above the legal size limit, and different size limits. And slowly they brought this area back so that now it all produces. And it was these experiences which began making me think how complex these natural phenomena, the natural, particularly shellfish. But over time I began, as I worked on other assessments of deep water fish and sharks and lobsters, many species, not at this small scale of abalone, but at larger scales, I began to see this same complexity. Areas where fishermen would stop fishing because now there was nothing there. And always you hear fishermen say, "Oh, they have moved to another place." The fishermen have moved, not the fish. The fish are gone here, and now you must fish there if you want to fish. And I began seeing it. At first I hoped this was just a problem of abalone, but now I believe it is, at different scales, a problem for many, many species. You know, the lobster biologist used to believe that the lobster in the southern hemisphere, the larvae, would travel right around the world for 18 months and settle back in their places they hatched. And then in the early 1990s, one fisherman found a lobster species that was only on 2 seamounts off Chile. And the lobster biologists went, no, they cannot go all the way around the world and find 2 seamounts. And so now there's been a genetic study done. And sure enough, they find the lobster species, they're staying within maybe 100, 200 kilometres of the adults. And nature has... thank you for being here, and to the people in the web, hola. Especially to Vanessa, who hopefully is in the middle of the night, is watching from Bali in Indonesia. So, hola, Vanessa. I hope the web in Bali is working for you. So here is an approximate outline of what I hope to talk to. Just giving some of the background of my interest and my development of my thinking about small-scale fisheries, and then explaining some of the concepts that underlie our new approach, how the size structure of populations changes as the fishing pressure increases, and then this fisheries concept called spawning per recruit, or SPR. And so that is some of the theory. And then I want to just talk about how searching for the answers for small-scale fisheries. We have, with Adrian, we've developed a new technique for analysing size data, just size data, which we think can simplify assessing fish stocks. And then hopefully I'll get time to talk a little bit about the work we're doing in Palau to illustrate how artisanal fishermen are coming to accept and to use this technique. So for me, this journey, and some of you I know were here 6 or 7 years ago when I was talking, so I hope this will not be aburrido for you. So for me, for my doctoral thesis, I had this question. In Australia, the abalone fishery is very valuable, and we were aware in the whole world that the production of abalone was declining, and we were wanting to conserve our fisheries and understand why in Mexico and the US and in Japan the catches were declining all the time, and we were wondering why it was so difficult to sustain abalone. So I first went and began talking to the divers and learning the fisher knowledge. I was also going to the library and learning the science knowledge. And in the science knowledge was that the larvae of the abalone would move 90, 100 kilometres. And my job for this state of Tasmania was to make an assessment for the entire state. Maybe 400, 500 kilometres of coastline. We were assuming was one stock. And the larva we thought was moving 100 kilometres. And we were expecting, we had one study of maturity and growth, and we were seeing this as a large, uniform fishery, just like the textbooks were telling us for many species. But when I talked to the fishermen, they talked about areas that kept producing and other areas that declined, and they could see these areas closely. Our statistics didn't show this because our statistics were from big areas. But the diver said, in this area, we no longer go there because there is nothing. We go here now. And they call recovery bottom and non-recovery bottom. Some areas produced, others didn't. And began asking my question, why? And so, this is complicated, but we can make it simple. So I set up an experiment where in these central areas I removed all of the adults. And in the other areas, the controls, we did nothing. They were controls. And we did it in these multiple places around the bottom of Tasmania. And these over here, this is all the different sites. But just focus, here is the summary on the right-hand side. So the first with the adults. Before we began, this was the average density of the adults. The two controls, and here the experimental area. So we removed the adults, we reduced the density of adults by this much. So this was the pattern in the next breeding season of adults. And when we came back, this is the pattern of, this was the pattern of the recruitment. So what we showed that on scale, not 90 kilometres, 100 kilometres, but on a scale of 60 metres, we could reduce the recruitment by the adults. And so what was important was the local amount of adults. It didn't matter that there were abalone meters, hundreds of meters or kilometers away. What mattered was the abalone were breeding close to each other and the larvae were staying in the one place. And so we began thinking, this is not one fishery, but every reef is a fishery. And to make, at first we began thinking, well, if the fishermen go everywhere and the abalone breed at the same size and grow the same way, then maybe that the larvae don't move is not so important. But what we saw, so here is a growth curve. This is actually for New Zealand, this information, but we saw the same thing in Tasmania. So here this is growth, this is age, and 3 different places. Stewart Island in the south, Banks Peninsula in the middle, and here Taranaki in the warm water. And each place has a different type of growth. And for abalone it is mainly about gears and complex mechanisms in the ocean that the biology takes advantage of to remain close to home. And so I think if we conceptually for all species, so here I'm showing the idea of this is the distance that animals are travelling through their life, and this is the proportion that travel. And I think that all species at different scales, for evolutionary reasons, they maintain long-distance dispersal because as the environment changes, as habitat is lost, the sea levels rise, they must always be able to find new places. You must have colonisation. But it is like us. A few people move a long way, but most people stay close to home. And so when it comes to managing, and I think we biologists, it is more exciting to look at the longest tag movements. How far did the animal, the record, what was the record? It is not so exciting to think about the average distance moved or the distance that most animals move in 1 or 2 years. But this is the scale that the management has to happen at. And I think when we look across all the species, over the last 20 years, we have been revising our estimation of what this distance is to smaller and smaller. You know, with tropical reef fish, we used to wonder how they could leave the atoll and go out in the ocean, and then how could they find another atoll? But now we know that if you take an area 400 by 400 meters, 60% of the larvae settling came from this area in the first place. They went outside the reef and they found their way back to this atoll and back to where the parents were. With the clownfish, more or less 30% of the clownfish coming to an anemone come from those parents. So finding, like the salmon, we know the Pacific salmon, not only find they go to the Bering Sea for 3 years, they not only come back to the river and the stream, they come back to the gravel bed that they hatched in. And so everything is more smaller and more complicated than we thought. And so for me, this is the challenge. I call it the tyranny of scale. That our management is still happening over hundreds of kilometres in most parts of the world. I think here in Galicia you're a bit different with many of your fisheries, and I think you are leading the world. But for me, this is the challenge that we face globally. That we are, in many places we are now starting to collect our data at a smaller scale, temperature. In a cool temperature, more nutrients, and they grow. You can see that because where this growth curve bends over is their maturity. So very different size of maturity. And what I'm showing here, this is the legal size. You can only take the abalone above a certain size. And so what you see is these populations here are totally protected. This report concluded, in this area, Taranaki up here, there is no commercial fishery, but there is a recreational fishery. This report concluded that in Taranaki, the recreational fishery is entirely illegal. The Bahoil Taye. But because this is the area that I was commercial fishing, mainly down around here, I know that all of these places, it is poor growth. It is small size maturity. If you come into this area, this beautiful area of rheas, and down on the exposed side of this island, Stewart Island, there are growth curves that are way, way above any that are here. And everything you can take. No, even when you fish legally, you can remove all of the adults. And so now this is the scale of maybe 1,500 kilometres. Now come down to this scale. This from here to here is 45 kilometres, and it is right here. This was when I was fishing here commercially. My house was just here, and this is a very, very exposed coastline, and here is very sheltered. And down here, on the exposed shoreline, the size of maturity is very big. And to begin with, we all fished there because it was easy, good catch rates. But after 15, 20 years, we had removed all the adults and all the larvae, and it was dead. The bottom was dead. There is a bay just in here where we used to take 5 tons per year. And in maybe 2001, the last time I went there, we found 5. Not tons, 5. But now, up in here, where we never fished because there are so many beneath the size limit, it was too hard work and not many that were legal sized, they are breeders, but breeding, they're adults, but they're small. And so now, all of the fishing occurs in here. And, but this is one statistical area. So the catch statistics say almost nothing has changed. And so now if we come to this scale here, this is 2 kilometres. And I had a fish